So projectiles. Let's start with a topical subject, drone, but less topical. It's dropping its payload. So here we have a situation where we've got an object falling under gravity, but it's flying or moving horizontally at 12 meters per second when it starts its fall. So I'm taking the origin as the point at which the mass becomes detached from the drone, and at that point it's traveling horizontally with a velocity of 12 meters per second. What I'm going to do is look at the vertical motion and take the direction, positive direction, as being the downward direction, simply because that's the direction that the mass will be falling. And because the acceleration due to gravity is constant, I can use SUVAT. The displacement, I'm looking at the 130 meters and looking at the object moving like that. So the displacement at the point where it hits the ground, or just before it hits the ground, the displacement is going to be 130. The initial velocity is 0. We're not interested in the final velocity. And the acceleration is 9.8. That's in the same direction as the positive direction that I'm taking here. And if I call the time that I'm looking for capital T, then those are the values that I've got for SUVAT. So I need the equation, the SUVAT equation, that doesn't have V in it, and that is this one. And when I put these values into the equation, I get that, and a little bit of clicking on the calculator gives me a time of 5.15 seconds. So that's part A complete. Now we need to look at the horizontal distance travelled by the mass while it's falling. So for this we're going to look at the horizontal direction. And horizontally the acceleration is 0. So I don't actually need to use SUVAT for this one. But if I did, then I would use the formula. I can use any one of the formulae really, because I know what T is, except any of the ones that's got S in it. So I may as well use the formula that I had for the first part. S equals ut plus half at squared. But like I said, we could use distance equals speed times time, because the acceleration is 0, and that's effectively what we get when the acceleration is 0. That term drops out, so we've got distance is speed times time. The time is this time here. So the horizontal distance is 61.8 meters. So that's part B complete. What assumptions have we made in answering these questions? Well, in order to apply SUVAT, we need to have constant acceleration, and that is very much helped if there is no air resistance. So by modelling the mass as a particle, we can remove the need to include air resistance, and also to worry about rotational effects. We've also assumed that the acceleration due to gravity is 9.8, and also that it doesn't hit anything else before it hits the ground. And knowing the way that Mike operates, he's a fairly lucky chap. Hopefully that won't be a problem. All right, so there we are. There's the answer to that question.